All right, everyone. Good news is we're almost to prisms. Bad news is we got to get through aberrations first. So stay awake, stay with me, and we'll get through this together. We're going to kick off this session here at the whiteboard talking about spherical aberration. And so here's a picture of a plus lens that I've drawn for us, and we've got light that's going to be hitting this plus lens. And a couple things that I want to talk about here with you is the key concepts behind spherical aberration. One of them is that you have two types of rays that we want to talk about, right? One of these rays are going to be called paraxial rays, right? And these are going to be the ones in the center. They're going to be the ones that hit almost to the axis of the lens or the axial point of the lens. So remember, paraxial, think close to the middle, all right? Paraxial. Now the rays on the edges, right? These rays on the edges, those are going to be our marginal rays, all right? Our marginal rays. So these are going to be our paraxial here in the middle. And then the ones on the edge are going to be our marginal rays. Okay? And here is the key take-home message about spherical aberration. Marginal rays are bent more. Right? So marginal rays, rays that hit on the edge of a lens, are going to bend more. So in a plus lens, they're going to come to point focus first, right? The paraxial rays going to come to a point focus second behind. All right? So key point once again, marginal rays bent more. Okay, there's a couple of points I want to highlight here in the text. So you've got this picture. If you want to pause the video for a second to draw this picture out, I think it'll hopefully help visualize spherical aberration while you're studying in your board's prep. Now we've come back here, we've got a few topics I want you guys to highlight here. So you guys see marginal rays in the text, rays on the periphery. Right above that where it says are close to the optical axis, or are not close to the optical axis, sorry, you want to write are bent more. So rays on the periphery, just right above that, are bent more. All right? Now that's number one in terms of our key points. Number two on our key points is under longitudinal spherical aberration, second sentence, marginal rays focus to a different location compared to paraxial rays. Right? And then go down one line where you see essentially, number three key point, a point object is no longer forming a point image, right? And then number four, go down a line to the right, it says longitudinal spherical aberration occurs for both on and off axis point sources. So just as a summary, your key points, marginal rays are bent more, they focus to a different place than paraxial rays, right? A point object no longer makes a point image because you get the marginal rays focusing here, the paraxial rays focusing here, and every ray of light in between those are going to focus at some point between those points, right? And so essentially what you get is you get this blur circle, right? And that's spherical aberration. And it also occurs for on and off axis point sources. So very key points there as we're moving forward. Two key points for coma that we want to have down. They're both in your text, so you can just highlight them, right? The first one, right, is going to be only for off-axis point sources, right? So it's off-axis only, right? That's going to be coma. The second one is if you go down two lines, you'll see an asymmetric comet-shaped blur. Right? So two key points for coma you want to keep in mind. Only for off-axis point sources, and you get an asymmetric comet-shaped blur patch with coma. Very good. Let's keep on going on to oblique or radial astigmatism. With radial or oblique astigmatism, a couple of key points to remember is number one, that both of those names mean the same thing. So radial, oblique, or also some people know that as marginal astigmatism. They all mean the exact same thing. But in the first sentence you want to highlight, this is all due to rays of light hitting a lens surface obliquely, right? So instead of light rays hitting on square, right, what happens is that light rays hit a lens obliquely, right? They come in at oblique angles, okay? And what happens if we come in obliquely is that instead of getting a line focus, right, we actually get several curved images, right? And we have three main ones with radial oblique astigmatism: tangential, right, our T, sagittal, our S, and Petzval, our P, right? And so we've got three main ones to look at. If you're trying to remember, and this may be a little bit too picky for the test, but if you're trying to remember, okay, what is the order of these, right? A way to be able to remember that is you have a teacup, right? A teacup, then you have a saucer, and then you have a plate. So you put a teacup on top of a saucer and then you put that on top of a plate. So that's one way to be able to remember that, just in case, you know, that's something there. But to be honest with you guys, that may be getting a little bit too technical, but I wanted to go through just because it kind of helps kind of understand this concept in terms of the big picture. So going back to your text, you got rays of light hitting a lens or surface obliquely, and then go down to the last line of that paragraph and you'll see, as a result, a flat object plane yields an asymmetrically warped image plane. And that's what we drew a picture of here, right? So we've got our warped images. Now, what is the key take-home message for you guys about radial or oblique astigmatism? How do we minimize it as optometrists, right? And how do we do that? By picking the correct base curve. That's exactly right. I hear you guys saying it through the computer, right? So look in your box right there in the text. You guys see that box? It says radial astigmatism must be considered in designing ophthalmic lenses. Highlight, it can be reduced by picking the correct base curve. So for picking the correct base curve to minimize radial or oblique astigmatism, we have this thing called the churning ellipse, right? This churning ellipse. And so if you look on the y-axis, and you guys will see this in your text, right? We have base curve here on the y-axis, and then we have back vertex power here on the x-axis, right? So the power of the lens, all right? And whenever you guys are thinking about churning ellipse, just think of it as like not having a T and a S, and it's churning ellipse, right? So real easy on that. All right, so the key point here is that we have two curves, right? One is the Oswald curve, and the other one is the Wallstrand curve, right? So which of these two curves do we use to try to pick for ophthalmic glasses? Which of these curves do we use to try to minimize oblique or radial astigmatism? Do we use the Oswald curve, right, which is the bottom curve, right? Or do we use the Wallstrand curve, which is the top curve? Yeah, that's exactly right. We use the Oswald curve, right? So the Oswald curve is what we use in optometry, right? So that's the key point. Can be minimized by a base curve, and typically we're going to use the Oswald curve is going to commonly be chosen because it's the flatter base curve of the two curves. And that's going to be in that text right there. You guys can highlight that. Oswald curve usually used to choose a base curve. Now, there's going to be two types of aberrations that we're going to be able to minimize by using the correct base curve. One of them, radial or oblique astigmatism. The next is going to be curvature of field. To help us better understand curvature of field, what I've done is I want to draw a picture here, and I've got an old school projector, right? So this is like the old school projector with the transparency, right? So for those of you guys that don't know what I'm talking about, pause the video, get on Google, you know, old school transparency projector circa like 1997, you know, back whenever me and Kyle were in high school. So, you know, you guys can look that up. You could also think of like a newer projector that would kind of work there as well. But anyways, the whole point is that if you can think back to those of you guys that have had these projectors in your past, it may have been in middle school, maybe in like elementary school, maybe, you know, maybe your college classes may have used something like this. If you go back to think about it, what happened is that you would have a flat transparency here, and instead of having a whiteboard like I'm able to do now with the amazing technology advances, right? What we would do is we would draw on the transparency on the projector, right? You'd have a little marker, and then what it would do is it would shine light up here to a mirror and then project that up on a screen, right? Now what happened is that if you think back, the middle of this, like the information, so whenever somebody would write something up on the screen, the middle was always really clear. You could see it, but the edges of that was always really blurry, right? And I always wondered why until I got in optometry school and we learned about curvature of field, and I was like, oh, that's why, right? Because curvature of field says that if you have a flat object like a transparency projected up on a screen, what's going to happen is you're going to get a curved image, right? And so part of the image is going to lie on the plane of the screen, and on the edges, this image is going to start to come off the screen. So by the time the light gets to the screen, right, it's going to be out of focus. So what you end up getting is you get in focus here in the middle, and then on the edges, you get information that is out of focus, right? And what's going to happen is the further you move this projector farther away from a screen, right, the more this image is going to be curved up, right, and the more out of focus the sides of the information is going to be, right? That's going to be curvature of field, right? And we can minimize that by two ways, right? One of the ways we talked about in terms of glasses to minimize curvature of field already was picking the correct base curve, right? What's another way that we could minimize curvature of field? Yeah, we could have a curved screen, right? And in our case, we have what? We have a curved retina, right? And so whenever we have somebody perfectly corrected with their glasses, right, or with their contacts, right, a curve corrected person, right, what happens is that image inside the retina will coincide. The image will fall inside the retina and coinciding with the retina, and everything will be clear, right? The next time you go to watch a movie, if you get there a little bit early, go up to the screen, right? And if you're in a pretty decently or a new movie theater, right, or a pretty decent movie theater, then what you're going to see is that they're actually going to curve that screen, right? And why do they curve the screen? Because they want to minimize curvature of field so that the periphery of your visual experience, right, is just as clear as everything in the center. Very good. All right, let's keep on going. Let's talk about distortion. Distortion results from the fact that magnification of a point object depends on the object's distance from the optical axis. So what you end up getting is magnification effects that change throughout the lens, right? So you want to highlight that in the text. And so if you go on to the next line, you'll see straight line objects form straight line images only if they pass through the center or the optical axis of the lens, right? And so that's kind of the optics behind it. But whenever we take this moving forward for boards, what I think the two key concepts you guys need to know is that there's two main types of distortion, right? So what are the two main types of a distortion? Yeah, we've got pin cushion, right? Pin cushion. And then barrel. Right? So pin cushion and barrel distortion. And so the important thing to remember about that is that each one of these is associated with a particular type of lens, right? So what kind of lens will give pin cushion distortion? Yeah, that's right. It's a plus lens, right? Count your P's, right? Pin cushion plus, right? And then a barrel is going to be a minus lens. Very good. So that is the key concept for you guys to have down. Pin cushion is made by a plus lens. Barrel is made by a minus lens. Excellent. Let's keep on going on to chromatic aberration. Chromatic aberration results from the fact that as light passes through a lens, right, different wavelengths of visible light are going to be refracted differently, right? So this is not going to be, I think, necessarily on boards, but you guys remember Roy G. Biv? Right, you guys remember that from like a physics class at some point in time in life, right? So your reds are going to be your longer wavelengths, your indigo and violets are going to be your shorter wavelengths, right? So the key take-home message about chromatic aberration, right, is that shorter wavelengths, right, your GBIV, right, shorter wavelengths are going to be bent more as they pass through a lens or optical system, right? And if you look in your text, you'll see that, right? Second line, you want to highlight exactly that sentence, right? Shorter wavelengths bend more as they pass through an optical system. So what does that mean? As visible light passes through a plus lens, what's going to happen is that light's going to be refracted down, right? That's going to be our green, right? Light's going to be refracted first. Our red is going to be refracted second, right? So in a similar concept of spherical aberration with the marginal rays and the paraxial rays, right? With chromatic aberration, green always comes to a point focus with a plus lens. Green always comes in point focus before red, right? Shorter wavelengths are bent more. Very good. Now, where does this come up into optometry, right? When do we ever think about this in optometry? Well, two key points, right? And if you look further into the text, you'll see a box there that says chromatic aberration underlies the use of the red-green spherical test in clinical refraction. That's a really fancy way of saying red-green balance, right? So whenever we think about red-green balance works because of chromatic aberration. Now, the other clinical usefulness for chromatic aberration is going to be Abbe value, right? It's going to be Abbe value. So whenever we think about Abbe value, we can quantify chromatic aberration by using the concept of Abbe value. So there's an equation here you guys want to highlight in your text. Chromatic aberration equals the power of a lens, right, over its Abbe value, right, which is a fancy V, okay? So the key point here that I want to highlight and why I bring this up here is not necessarily that, that this is a hard calculation, but that F, the power of a lens, is often forgot whenever we're talking about chromatic aberration, right? I think all of you guys would say, okay, if we increase our Abbe value, right, what happens to chromatic aberration, right? It decreases, right? We know that they're inversely related, right? We know that. But what happens if we increase our lens power, right? What's going to happen to chromatic aberration? Yeah, it's going to increase, right? So let's write this out to the side of our equation because I think that's the key take-home message. I think we all remember that Abbe value is inversely related to chromatic aberration, but a lot of times we forget that lens power is directly related to chromatic aberration. All right, just in case you forgot what I look like, I thought I'd come back here in front of the camera to finish this session talking about achromatic doublets. So we've been working at this whiteboard for a long time. You guys, you did an awesome job with this video. We're almost done with aberrations. Great work. Achromatic doublet here is continuing the stop process of chromatic aberration. It's a way for us to be able to minimize or eliminate chromatic aberration, okay? And so what we do is we take one lens with a certain chromatic aberration, or certain Abbe number, and a positive lens with some Abbe number. We take a minus lens with another Abbe number and we sandwich them together so that they eliminate chromatic aberration, right? Each of them separately would have chromatic aberration, but whenever you put them together, they cancel each other out and you get no chromatic aberration. Kind of a technical point, but I wanted to highlight that here in the text as well. Guys, great job with aberrations. Go dominate the quiz and I'll see you on the other side in Prisms.